Hi guys, in this video and next video we're going to run some hypothesis testing, and we'll start with something that we're familiar with, the testing on the testing for single restriction on single parameters in this video. And you introduce the linear hypothesis function from the car package, which is not necessary for the single restriction case, but is necessary for multiply restriction case. So let's begin with a right tail test on intercept, and we would like to test whether what's it called, the null hypothesis that the intercept is smaller or equal to 0 against the alternative that the intercept is greater than 0. As the hypothesized value is 0, so we could simply use the t statistic that reported from R directly. We do not, or alternatively, of course, you could calculate the t value by using the coefficient estimate and standard error. But we could, in this case, we could simply extract the t value. As it is the first row and the third column is going to be you can state that the index equals to 1 before the comma and 3 after the comma. And the unfortunately the p-value reported in R is for two-tailed test, so we cannot use the p-value explicitly. We have to use the pt function in order to calculate the shaded area on the right hand side of the shade on the regions, and then we can calculate the p-value, which is 66%. It exceeds the 5% significance level, so we cannot reject the null hypothesis that the intercept is smaller or equal to 0. So alternatively, we could use the linear hypothesis functions. So when you call this functions, the first object you need to provide is the LM object, which is the regression that object we define, we call for in the previous videos. And starting from the second argument is going to be the restrictions that we want. So in this case, we would like to test the intercept. We would like to test the right tail test on intercept, but unfortunately, this function can only provide the two-tail test. So we will first say that the intercept is equal to 0, which is going to report the two-tail test p-value, and also have the f statistic. But we can then use the f statistic to get the p-value for the right tail as well. Yeah, actually, I would just like it's going to get the same thing, but I just want to focus on the how to get the p-value from f distribution explicitly. So first of all, we are going to extract the f statistics from the output. As you can see that it's going to be the second row, fifth column from the output. So it is going to we are going to save it as the we just extract the f stat and save it as and name it as f underscore stat underscore 1, and then we're going to use the pf functions to and provide this f statistics as the first arguments, and the second argument is the number of restrictions, and the third argument is the degree of freedoms for the unrestricted model. So if we recall the regression model, we can see that the unrestricted regression has 83 degrees of freedom, so its degree of freedom is 83. And then if we calculate the p-value, we can verify that it is exactly the same as what we calculate. So this is the right-tailed test, and now let's try a two-tailed test for the on beta 1 estimate. So this one is going to be more straightforward. Like we would like to test the null hypothesis that the beta 1 is equals to 1 against the alternative that it is not equals to 1. So this time we have to extract the coefficient estimate of beta 1 and standard error of beta 1 explicitly from the second row of first column and second row of the second column. And then we're going to construct the test statistic by providing the hypothesized value, and then we're going to use the PT functions again, and then we're going to get the one side the shaded area of the one side, and then by exploding the symmetric properties, we're going to get the p-value as the 0.0017, which is smaller than 5% level, and we can reject the null hypothesis that beta 1 is equals to 1. So it is quite straightforward to verify in this case using the linear hypothesized function. Again, for the first object, we're going to provide the LM object, and the second argument, we're going to provide the test that we want to do. So this time is directly with showing the p-value is going to be 0.00175, which is the roundup of the p-value reported from above. Of course, you could choose to calculate explicitly by extracting the f statistics from the linear hypothesized function, which is 10.4622, and it is because it is round up when you print out the output. And then you could use the PF functions explicitly, and you can see that like each of this is the f stat, and each way is going to report you the same thing. The p-value is quite straightforward, like for two-tailed tests. So let's do one more example for single restriction on single parameters, and we're going to test whether beta 1 is equals to -1 against the alternative that beta 1 is not equals to -1 as the theory state. So we're going to extract the actually, we do not need to repeat this step again because we just did it in the second case. But we do need to calculate the test statistic explicitly, but because the hypothesized value is different now. And then we're going to use function PT again to get the shaded area of one side, and then times 2 to get the shaded area of both sides, and then this is the p-value, which is 0.96, which is 96.6%. That like we cannot, which is way larger than 5%, so we cannot reject the null hypothesis that the beta 1 is equals to -1. So, and again, like we can verify using the linear hypothesized functions. The first argument you provide is the LM object m_1, and you're going to change the second argument by from 1 to -1 compared to the second case. And again, you can see that it can be verified by the p-value. So you could just repeat these again. Actually, I don't know why, but this is the degree of freedom. This is for the unrestricted model. Oh, sorry. Yeah, and you can verify the p-values using these.